Welcome to section 11.3. Today we're going to continue talking about identities for our trig functions, but today we're specifically going to focus on sum and difference identities. So in the last unit we talked about the Pythagorean identities. These are going to be sum and differences, where we are either adding or subtracting different angles within our trig functions. So let's go ahead and dive right into these sum and difference identities. Alright, so let's take a look at a quick example here about what we're going to talk about today. We want to ask ourselves, is this true? If we were to take the sine of a 45-degree angle plus a 30-degree angle, is that exactly the same? Is it equal to if we were to take the sine of 45 plus the sine of 30? So I know a lot of us, whenever we see something in front of a parentheses, we think about distributing it. That's what we're testing here. Is it true? Can we distribute the sine function to the 45-degree angle and the 30-degree angle to give us this? Okay, so we're actually questioning this. I don't know if it's true or not, but we're going to determine, can we actually do that? So let's bring up our calculator and maybe do a quick proof here. Can we actually do this? So let's see, my calculator's a little too big. Make it a little smaller. There we go. Alright, so if we were to do sine, let's make sure our calculator's in degree. Good thing I checked, because it's in radians. So we'll change that. Alright, so sine of 45 plus 30. I'm going to type it in exactly how I see it, and if I were to do sine of 45 plus 30, I would get a value of 0.9659, so on. Okay, but now we want to check, is that exactly the same if we were to do sine of 45 plus sine of 30? So I'm going to type this in exactly how I see it. Sine of 45 plus sine of 30. Do we get the same exact answer, the same decimal representation? And we actually don't. Okay, so take a look at that. Notice how they are not the same. Maybe we will, there we go, screenshot that. So notice how they're actually not the same. So this distribution that we thought we could do, we actually can't. Okay, so we cannot distribute. The sine of 45 plus 30 is not equal to the sine of 45 plus the sine of 30. So what's going on here is how we have specific sum and difference identities. In this case, we were looking at a sum example because we were adding things together, but this would be the same case if it was subtraction. So sine of 45 minus 30 would not equal sine of 45 minus sine of 30. So sum and differences, kind of either adding or subtracting here. So simple distribution is not the way to go. We specifically have these rules, these identities, about how we need to either add or subtract two angles together, either in a sine, cosine, or tangent trig function. So these are the sum and difference identities. I know that's kind of crazy, a lot going on here, but I'm just going to give these to you. Okay, so if you're really interested on why the sine of alpha plus or minus beta is equal to the sine alpha cosine beta plus or minus sine beta cosine alpha, if you really want to know where that came from, just let me know. I'll show you a proof, kind of explain to you why we have these. I figured a lot of us just like to take things the way they are, so I'm just going to give them to you now. But if you're really interested, you really want to know where these come from, just let me know and I'll be very glad to show you how these work. We're going to talk about how they work today, but rather where they came from. So in this case, let's talk about these really quickly here. If we were to take sine of some angle, okay, that's what alpha and beta mean, just like 45 degrees and 30 degrees here. If we were to take some angle plus another angle, specifically when we're dealing with sine, it's going to break down in this fashion. Remember, we cannot distribute, so we're going to have another way of calculating this sum of the sine function. So we take the sine of the first angle times the cosine of the second angle, and if we're initially adding these two together, we're going to initially add these two pieces together. Same thing here, if we are subtracting these two angles together, we're going to subtract these two together. So whatever is up top in the original, you follow whatever's up top in the identity. So for cosine, if we're adding these two angles together, we would break down this addition of angles in this fashion. The cosine of the first angle times the cosine of the second angle would mean we subtract the sine of the first angle times the sine of the second angle. So notice how in sine everything matches. If you're adding them together, you're adding the two pieces together. But cosine's a little bit opposite. If you're adding the two angles together, you're actually subtracting the two identities together. Tangent kind of follows sine here. If we're adding the two angles together, we are adding the two angles up top, but we are subtracting the two pieces or identities on the bottom. So just be careful you're following these exactly how they show up. If you need help using them, don't be afraid to ask, but we're going to do a few examples in this lesson just to get used to using these sum and difference identities. Alright, so let's go ahead and take a look at our first example here. We want to try to calculate cosine of 15 degrees. Now, hopefully we notice how 15 degrees is not one of those key angles that show up on our unit circle. We had 30, 60, 45, 90, 180, 270, 300, 150. All these different angles are showing up on our unit circle, but 15 degrees is not one of them. So what we're going to end up doing is rewriting 15 degrees as either the sum of two angles that show up on our unit circle or as a difference of two angles that show up on our unit circle. So there's different ways you can do these. Either you can add angles together to get this, or you can subtract angles together to get this. That's why they're called sum/difference identities. You can use them interchangeably depending on which one you're more comfortable with or which one best fits our example. So let's think about 15 degrees. How can we take two of our unit circle degree measures and either add or subtract them together to get 15 degrees? Well, if you think about it for a second, we could take cosine of 60 degrees, which is on our unit circle, and subtract 45 degrees, which is also on our unit circle, and we would end up with the 15 degrees that we're actually trying to find. So we know based on our unit circle what the cosine of 60 degrees is and what the cosine of 45 degrees is. We're going to subtract those according to our, in this case, difference identity, because we're subtracting, in order to figure out what the exact value of cosine of 15 degrees would be. So these are the two angles that we're going to focus on. So we're focusing on specifically cosine, so we're going to use this identity. And since we're subtracting two angles together, we're going to use the bottom operation here. So since we're subtracting, that means our identities that we're going to use need to be added together. So cosine of one angle minus another angle will be broken down into this fashion. So we got to take the cosine of the first angle, which in our example was 60. And we're going to multiply that by the cosine of the second angle, beta, which in this case was 45 degrees. So cosine of the first times cosine of the second, and we're going to add sine of the first angle, which was 60, times sine of the second angle, 45. Okay, so that's how we break down this initial cosine of 60 minus 45 into this identity. So now notice how we're no longer using cosine of 15, we're using cosine or sine of 60 or 45. And according to our unit circle, we know these exact values. Cosine of 60 is 1/2. Cosine of 45 is the square root of 2 over 2. If you need to use your unit circle to kind of reference these, you can. However, I'm kind of expecting you to know these or at least be able to draw the unit circle yourself to help you figure these out. So you should begin to start to remember what these specific angle measures and their exact values are. Sine of 60 is the square root of 3 over 2, and sine of 45 is the square root of 2 over 2. Alright, so now let's simplify this. We're multiplying two fractions here together. Multiplying fractions, we go straight across, so we're left with the square root of 2 over 4. Over here, if we go straight across, we have the square root of 6 over 4. Notice how we're adding fractions, and it's nice already that they have... having a little technical difficulties there, I guess. Like I was saying, it's nice that they already have a common denominator of 4. That means we can simply add the numerators. So we have the square root of 2 plus the square root of 6 over 4. Okay, just as a little side note, the square root of 2 plus the square root of 6 is not equal to the square root of 8. Okay, this is a no-no. These are not like terms. I know they're both radicals, but the square root of 2 plus the square root of y is, 6 is not the square root of 8. They are not the same radical. If it was the square root of 6 plus the square root of 6, we could say 2 square roots of 6 because we have 2 of them, but this is a no-no. We got to keep them separate. It's almost like if we had x plus y up top, we would keep it x plus y. So in the end, the exact value of cosine of 15 degrees is the square root of 2 plus the square root of 6, all divided by 4. And if you actually want to check that out on your calculator, you could, just to see if you were correct. If we do the cosine of 15, notice how we get 0.96592 and so on. So that's what we know this should be as a decimal. Let's type this in exactly how we see it. Now since we have a fraction, we should put the entire numerator in parentheses. So we have the square root of 2 plus the square root of 6, all divided by 4. And notice how our decimals match. So this is an exact answer for the square root of, the cosine of 15 degrees. Alright, so let's check out another example. Same idea here with the sine of 105. Notice how 105 is not one of our main angles on our unit circle. So we're going to have to break down 105 either into two angles that add together to 105 or two angles that subtract from each other to give us 105. Remember that sum or difference idea. So let's think about, maybe the last example we did was a difference. Maybe we'll do an example of a sum for this one. So two unit circle angles that add together to 105 would be 60 and 45. Happens to be the same two we did before. But this time we're focusing on sine, and we are adding two angles together. So according to our identity, we're going to be adding these two pieces together. So the sine of two angles being added together is equal to the sine of the first times the cosine of the second. And since we're adding our two angles together in the sine function, we're going to add the two pieces together in our identity. Next, we're left with the sine of the second angle times the cosine of the first angle. So now that 60 and 45 are nice unit circle degree measures, we can break them down into their exact values. Sine of 60 is the square root of 3 over 2. We're multiplying that by the cosine of 45, which is the square root of 2 over 2. Now let's add our second piece. Sine of 45 is the square root of 2 over 2. And cosine of 60 is 1/2. So notice how we're multiplying some fractions on the left and on the right. Let's multiply straight across. We get the square root of 6 over 4 plus the square root of 2 over, that should be 4. And notice how, again, we are adding some fractions. So common denominator already checks out. We can simply add the tops together. Square root of 6 plus the square root of 2. Remember, they're not like radicals. One's a 6, one's a 2, so they got to stay separate. And we keep the common denominator of 4. Again, you can check your answer. Sine of 105 in your calculator, turn it into a decimal. Should match this fraction when you type it into your calculator and get a decimal as well. Alright, so far we've done a cosine example and a sine example. Let's try a tangent example, and we're even going to throw in radians. So just because I know we like degrees, okay, I am going to throw in radians, but I need to clue you into kind of a confession, if you will. I am a complete fan of degrees, okay? Don't get me wrong, I know what radians are, I know how to use them, okay? I'm familiar with fractions, I know how to deal with fractions, but my mind just works in degrees for some reason, okay? So, and I know some of you may be like that as well. So if you would rather convert this into degrees and maybe do something very similar to how we did in example 1 and example 2, go ahead and do that. Actually, that's what I'm going to do when we go through this example. But if you would rather work in radians, some of you might be more comfortable or familiar with that, please go ahead and use radians. But for my purposes, since my brain works in degrees, I'm going to convert 11 pi over 12 into degrees. So to convert from radians to degrees, we got to multiply by 180 over pi. Notice how the pi's are going to cancel because we've one up top, one on the bottom. And if we simplify our fraction, 11 times 180 all over 12, we're going to get 165 degrees. So really, we're focusing on the tangent of 165 degrees instead of 11 pi over 12. They mean the exact same thing, it's just we started with radians, but I'm converting it to degrees just because that's how my mind works. Again, you can use radians if you'd like to. It works the same way. Whether you're dealing with 165 degrees or 11 pi over 12, you need to find two angle measures that either add or subtract from each other to give you this measurement, either in radians or degrees. So since I'm going to work in degrees, let's go ahead and focus on the 165. Let's think about two angle measures on our unit circle that can either add or subtract to give us 165 degrees. Off the top of my head, I think of 120 plus 45 degrees. So I'm breaking down this angle measure that we don't know into two angle measures that we do know. So tangent of these two angles being added together, notice how that's the top operation, means we're going to focus on the top operations in our identity. So this ends up being tangent of our first angle, which was 120, plus tangent of our second angle, which was 45 degrees. And that's all over 1 minus tangent of our first angle, 120, times tangent of our second angle, 45 degrees. Alright, so we should know these exact values. Again, you can use your unit circle in your mind. Maybe you got to write it down to reference. But tangent of 120 is negative square root of 3. Tangent of 45 happens to be 1. So we're going to add those together. Now, let's check out the bottom. We have 1 minus, we already know tangent of 120 is a negative square root of 3, and we're going to multiply tangent of 45, which is 1. Now, let's see what we have here. We have negative square root of 3 plus 1, and up top, now on the bottom we have negative square root of 3 plus 1, which is a negative square root of 3, but if we're subtracting a negative, it actually changes to a plus. So we have 1 plus the square root of 3. So that's as far as we can go when we simplify it, but notice how we have a square root in the denominator, and we cannot have a square root in the denominator. Normally, if we have like 1 over the square root of 2, we've been multiplying by what's in the bottom to get rid of it, to rationalize it, and we would be left with something that no longer has a square root in the denominator. But so far, oops, I didn't mean to do that, technical difficulties again. What we talked about something this year that, let's say we do have a square root in the denominator, but there's another piece to it. Notice how we are adding this 1 on the end. To get rid of a square root in the denominator that has another piece with it, we need to multiply by the conjugate, which is when we simply just reverse the operation that we're doing. So if this is 1 minus the square root of 2, we need to multiply by 1 plus the square root of 2. Hopefully some of us remember doing that. We've actually done it this year. You might need to go back and look at it. I think it was in Unit 6. Might be wrong, but I think it was in there. So let's multiply this guy by the conjugate. Instead of 1 plus the square root of 3, we want 1 minus the square root of 3 up top and on the bottom, keeping our fraction balanced. So let's see what we get when we do our distribution here. We have this quantity times this one. So negative square root of 3 times 1 is negative square root of 3. Negative square root of 3 times a negative square root of 3 is a positive square root of 9, but the square root of 9 is 3. Now let's do our inside one. 1 times 1 is 1, and 1 times negative square root of 3 is a negative square root of 3. Now if we check out our denominator, again we have this piece times this one. 1 times 1 is 1. 1 times a negative square root of 3 is a negative square root of 3. Square root of 3 times 1 is a square root of 3. And square root of 3 times a negative square root of 3 is a negative square root of 9, but the square root of 9 is 3. Alright, so now let's start to simplify this. 3 plus 1 is 4. Notice how we have this square root of 3 minus this square root of 3. Those are like terms. They're both a square root of 3. So if we're subtracting them together, we're subtracting 2 over all. We have minus 2 square roots of 3. Now if we check out our denominator, 1 minus 3 is a negative 2. But we have a negative square root of 3 plus a square root of 3. Those are going to cancel each other out. So starting to break down a little bit here. And let's do some division. We have 4 divided by negative 2, which is negative 2. But then we have this negative 2 divided by this negative 2, which is a positive 1. And we're left with that square root of 3. So in the end, if you want to check your answer here, tangent of 11 pi over 12 would simplify to negative 2 plus 1 square roots of 3. Alright, let's check out example number 4. Write the expression as the sine, cosine, or tangent of an angle. Okay, so of an angle means a single angle. Take a look at what we have here. This is kind of like what the identities look like, where we're taking sine or cosine, multiplying them together, either adding or subtracting them in the end. So if we take a look at what this statement looks like, let's compare it to one of our identities. Notice how we're specifically taking a sine angle and multiplying it by a cosine angle. If we look at our identities, which one of these kind of matches this format? Well, notice how that's the sine function, where we're taking the sine times a cosine. That's exactly what we have here. Cosine takes cosine times cosine, and then sine times sine. They kind of stay with each other, but with the sine function and the sum and difference identities, they are mixed up. So we're actually looking at a sine expression here, not cosine or tangent. So let's take a look at this. According to our identity, we have the sine of the first angle times the cosine of the second angle. So in the end, if we're going to write a sine function, we're going to need sine of 42 and 17. But the question is, are we adding those together or are we subtracting them? Okay, we got to take a look at the symbol that we're using in the identity. Notice how between these two pieces, we are subtracting them together. So if we look at our identity, that is our bottom portion here, which means in our original sine function, we were subtracting them as well. So we should be subtracting 42 from 17, which would give us a sine value of 25 degrees. So really that question is just telling you to analyze these different identities, try to, instead of break it apart like we've been doing in our examples, we're trying to figure out what were we originally finding. Alright, let's take a look at example number 5. Find the sine value of x minus y given the following. Okay, so we're having some information here. It kind of looks like a lot, but it's really that, or not that difficult when you break it down and look at each piece individually. So over here, they tell us that the cosine of x is equal to negative 3 over 5. Remember, this is the ratio of the sides of a right triangle, so maybe we should draw a reference triangle within this radian measure. And over here we have the tangent of y is 8 over 15. Again, this is a ratio of the sides of a right triangle. So, and it's going to be in between these measures over here. Now, let's be careful here. I think this should be negative 8, actually. Okay, we're going to make that negative 8. And you'll find out why when we draw our right triangle in a second. Okay, so let's take a look at this. Cosine, if we draw our reference triangle between pi over 2 and pi, so that's going to be somewhere in here. So here's our angle of x. And cosine is adjacent over hypotenuse. So we have negative 3, which is the adjacent, over the hypotenuse, which would be 5. Using the Pythagorean theorem, we can figure out that this side is actually 4. Now let's draw a reference triangle over here for tangent. 3 pi over 2 and 2 pi is somewhere in here. So here's our angle y. And tangent is opposite over adjacent. So this h should have been negative because if it's opposite, notice how this piece is going down. It should be negative 8. And then the adjacent is 15. Okay, we're going positive 15 to the right. So there's our reference triangles. We want to figure out sine of x minus y. So maybe we'll write that out. Sine of x minus y. And according to our identities, if we are subtracting a sine value, let's break it apart into the appropriate identity. We need sine of the first angle, which is x, times cosine of the second angle, which would be y. And we're going to subtract sine of the second angle, which is y, times cosine of the first angle, which is x. Now it's really going to be simple for us to find these sines and cosines values now that we have our triangles to help us out. So let's find sine of x. That's this triangle over here. Sine is opposite over hypotenuse, so sine of x would be 4 over 5. Now let's find cosine of y. That's this triangle over here. Cosine is adjacent over hypotenuse, so we would need 15, and the hypotenuse would be 17 if you did Pythagorean's theorem. So we'd have 15 over 17. Now we got to subtract sine of y. So in our y triangle, again, sine is opposite over hypotenuse, so we need negative 8 over 17. And cosine of x, going back to our x triangle over here, cosine is adjacent over hypotenuse. And notice how they kind of already gave that here. We have negative 3 over 5. So just like before, we have fractions times fractions. Let's multiply straight across our fractions. We're going to get 60 over 85 minus 24 over 85. What's nice now is that since we're subtracting fractions, we actually have a common denominator, which means we can simply subtract the tops, which would give us 36 over 85. So if we were to take this triangle and subtract it from this one, and specifically look at the sine value when we did that, our opposite side would have a length of 85, and our hypotenuse would have a length, our opposite would have a distance of 36, and our hypotenuse would have a distance of 85. Last but not least, let's take a look at example number 6, is the equation an identity? So it's basically asking you to prove, is this true? Do we actually, if we were to take tangent of x minus pi, would we actually get out tangent of x? Almost like what we've been doing in the last few sections or lessons, trying to prove these identities. We want to prove this. But since we're dealing with a difference here, we're subtracting two things together in a trig function, we should focus on maybe our difference identity for tangent. So taking a look at our left-hand side here, we have tangent of x minus pi. Since we are subtracting those two pieces together, let's subtract our numerators and then add our denominators when we break it apart. So if we were to use the difference identity for tangent on our left-hand side, we would have tangent of x minus tangent of pi all over 1 plus tangent of x times tangent of pi. And we want to try to ask ourselves, does it equal tangent of x? We're trying to figure this out. Are they the same exact thing? Well, notice how tangent of pi, we can actually figure that out based on our unit circle. Tangent of pi is 0. So we can fill in that value for tangent of pi's. Again, does it actually equal tangent of x? What we're trying to figure out. Tangent of x minus 0 is just tangent of x. And notice how down here in our numerator, we have 1 plus tangent of x times 0. But anything times 0 is just 0. So really this tangent of x is disappearing and it's becoming a 0. So 1 plus 0 is just 1. And anything divided by 1, notice how we have tangent of x divided by 1, anything divided by 1 is just itself. So really the left-hand side simplifies the tangent of x, and that's what we were trying to prove. So yes, it is an identity. Yes, it simplifies to tangent of x. We've done our job. So good luck on the practice and the application and the mastery check. Good luck. Don't be afraid to ask for help. And I'm going to end some things off here with a clip from the Wheel of Fortune, because we started with Wheel of Fortune. Hopefully we don't make silly mistakes like this guy does. Are not going to lie, they're actually kind of bad. But just check it out and maybe laugh for a little bit.
Pick that up, turn it over, lay it down right over that London trip down there. 650.
Y.
There's a Y. 500.
G.
1G. 700.
C.
Yeah, there are 2 C's. Well. Wow. Okay.
I solve.
Oh, well, that'd be a good idea, yeah.
Mythological hero Achilles.
I can't accept that.
Okay.
Shelby.
I'll solve.
Yeah.
Mythological hero Achilles.
Yeah, that's it. Oh, boy. Well, boy, when it comes to names, well, you have to just go with the name. And even though the letters are up there, because you have to solve it, which is what you did. You have to say it. And you said it. You get $1,000, which is house minimum, so you have 1,000. But we'll just wipe that clean from our memory bank and take a break and be back and play some more. Don't let that throw you the rest of the way. Wow.
L.
There's an L. Pick it up. You got both halves. So, 450.
D.
Yeah, there's a D. 300.
C.
Can I
Shelby?
solve?
Yeah.
The world's fastest man.
Yeah, that's it. We've had a couple of interesting ones. Laura,
C.
1C. Julia, everything just follows.
Let's solve.
Go ahead.
On the spot dice spin.
No. Shelby?
On the spot decision.
Yeah, that's it. I don't think anyone has ever taken a more circuitous route to victory. But the important thing is you're here. You got $11,700, and we're pleased about that.